Yeah, so I have started the recording. Okay, so it's 6 o'clock now. So let us begin with today's class. So first of all, wish you all a very happy Independence Day. So we have completed 76 year of independence and we are marching into the 77th year. So yeah, so happy Independence Day. So mainly today's class we will be focusing on the week 3 contents, which are mainly based out of uh, different discretization schemes, and then how do we analyze these different discretization schemes. Okay. So first of all, just recap the contents of your week 1 and week 2. So okay, thank you. So week one, we were mainly introduced to what is CFD and what are the various application areas of computational fluid dynamics. And then once we got a in motivation to kind of study the course, then we saw what are the different governing equations which are mainly present. By solving which we can get the flow variables, the velocities and the pressure. So that is the main interest we want to understand how these flow variables are changing, so that we can understand the uh, main situation, and then from these flow variables we are able to calculate some parameters like the lift coefficient, through which we can understand whether our design is proper or not. Okay, so then we can optimize our design. So that is the main inspiration motivation, I would say, behind studying CFD on an application level. Okay, so after going through the governing equations, we were mainly looking into how we can non-dimensionalize, but before that we also studied why to non-dimensionalize, and then we studied the non-dimensional governing equations. And then once we saw the equations, we learned that okay, the equations behave differently and we need to analyze the differences in the equation so that we kind of come up with a correct discretization scheme, correct time marching and discretization schemes. Okay, so you saw the characteristics of equation. We kind of categorize the equations into three different categories: the elliptic, the parabolic, and the hyperbolic equations. So mainly today, I will just touch upon how you can go about discretization for different of these characteristic equations, like different characteristics of these equations. Okay, so that is very important, because if you choose a wrong scheme, then you will end up with divergence. Okay, so you will not get a converged result, that is, you will not get a correct result. Okay, so you need to understand the characteristics of equation and then properly select a discretization scheme for that. Okay, so that is why we had learned the characteristics of equation, and then finally in the week one we also studied some benchmark problems. Okay, so the benchmark problems are those problems whenever like you develop some solver, you have to see whether your solver is working properly or not. So for that you kind of test it with some problems. Okay, so that those set of problems, they are called as benchmark problems. That was all about week one. In week two we slowly stepped into the domain of discretization, like uh, what is the first step. Okay, that is a pre-processing step in CFD. Okay, that involves generation of geometry and then a suitable grid for that geometry. Now what is grid, we already discussed in the last week. We try to divide the whole domain into a small number of parts wherein we can apply the conservation equations and then try to get the solution over those small parts. So the main thing behind all this thing is a continuum approximation, which you might have already learned in the fluid mechanics. Uh, so that we assume that all the molecules which are present in that particular one control volume which you take, they move as a continuous unit. Okay, so they have one specific velocity, okay, specific pressure. Okay, they move in continuum. That is the main assumption which we had made. That is there from your fluid mechanics itself. Okay, yeah. So mainly the grid generation part. So the structured and the unstructured grid. Okay, why we do that? Ultimately, we have to convert the partial differential equations into the linear algebraic equations. So that is called as discretization, and we kind of do that on single small elements in a whole domain. That is why you need to generate the grid. Okay, then once you generate the grid, how do you convert? Once you generate the grid, how do you convert these partial differential equations into a linear algebraic equation? First, we saw the Taylor series. So how we can expand one particular function. If we know the function value at say x, then how do you find the value of the function at x plus delta x using Taylor series? How do you do that? And from that we came up with an approximation for df by dx in terms of f at x, f at x plus delta x, which are our grid points, okay, in CFD. Okay, so we tried to see how we can convert this df by dx into f at some discrete points basically. That is the whole key here. We are trying to write everything in terms of some discrete points, the values at discrete points. Okay, so that is why we saw Taylor series. Okay, so once we saw Taylor series, then again the variations of that, the finite difference schemes, and what is the order of accuracy and how we can improve the order of accuracy. That was the main thing, and then we extended finally for non-uniform grid also. Okay, so till this it was week 1 and week 2. Okay, so mainly in week 3, uh, so just let me share my screen and then maybe revise the contents of week 3. Okay, yeah, so is my screen visible? Can you write on the chat box? Okay, so if you people have gone through, I hope you might have gone through the weekly contents. Can you also write on the chat box what was covered in week 3 mainly? I mean, it's already there on the in the title, but let me just see what else you have got to say in the week 3. What was the main thing? What were the main things which were covered? Yeah, properties of numerical schemes. Yes. Apart from that, in the beginning, what did we see in week 3? I mean, in the beginning of week 3, uh, just error and error analysis. Yeah, so those things were at the end of the week 3, I guess. The properties of the numerical scheme and the error analysis. In the beginning, I think we saw what are the different discretization schemes first. Okay, so just let me come here. So discretization, so first of all, why discretize? I have already given the answer for this. Okay, just let me go into the full screen now. Okay, so first we saw about discretization, why we have to discretize to convert the PDEs into linear algebraic equation. Then we saw mainly three types of discretization schemes: the finite difference, finite volume, and to some extent an introduction of finite element was also given. And when we go on to finite volume, you can have different grid types, which I will come across again during your questions. Okay, the first question I think is based on the grid types. Okay, that time I will mainly cover these grid types. Okay, so what was the main difference between the finite volume and finite difference? Can you just write down on the chat box? The what was the main like kind of at least the philosophy wise, what was the main difference between the finite difference and the finite volume? And write down on the chat box. Hmm, okay, finite volume is an integral form. Finite differences. Finite difference method uses the differential equation expansion based on Taylor series and finite element. Does FVM uses okay integral equations? Yeah. So to some extent, you all are absolutely right. Okay, so finite difference method, we directly take the partial differential equation and then directly apply the Taylor series expansion, which we already covered in last week. Okay, so that is the main thing. So we take the partial differential equation. Say for example, we have dfy by dx, dfy d square fy by dx square something whatever it is, d square f by dy square. So we just directly expand it in the grid points. Okay. So just to highlight. So if we have a domain something like this, we discretize into different grid points. So that is the key technical term. Okay, so something like this. So all these intersection points, these are called as grid points here, and on just this grid point we directly write the value of say df by dx direct using the Taylor series. Okay, direct in the differential governing equation. Whereas finite volume method is of a more physical method, I would say. I mean, uh, it has a physical intuition uh, that we take the same domain, we do the division in the same way, but this particular box we call it as a control volume. Okay, and then once we get a control volume, what we say is that the governing equation should, the conservation equation or the governing equation, that should be satisfied in this control volume. So over the whole control volume we integrate the differential equation. Okay, and say that okay, so this differential equation, it should be valid over the whole domain. Okay, so that is how we kind of come up with the equations, linear algebraic equations in the finite volume method. Okay, so whenever and we try to convert these terms, like for example, if you have say something like dou square f by dou x square. Okay, these are diffusion terms. So we try to come up with the flux based terms here, flux which is going out, flux which is coming in, okay, from east to west. We try to convert the linear algebraic equations but with a physical meaning. Okay, that kind of physical meaning is I would say not very much present in finite difference method. And it becomes, once you learn kind of finite volume method, it becomes very easy for you to kind of discretize any kind of equations. And even if you have like a just a physical governing law, you can also come up with the discrete equations for that physical governing law, even though if you don't have the partial differential equation. So that is one advantage. So what is the other main advantage of using finite volume method over finite difference? Can you write on the chat box? What is the advantage of using finite volume over finite difference? One thing I have already told, it has a physical meaning, it is an intuition. Okay, without even governing differential equations, we can try to come up with the discrete equations. Okay, but what is the other advantage of using FVM? Can you write down on the chat box? No, we when we try to do this discretization of dou square f by dou x square over a control volume, ultimately we kind of end up, as I said in the last week. Okay, ultimately we end up with dou f by dou x at east face and minus west face or something like that, when we even when we do the this control volume integration. So again here we have to kind of use the Taylor series expansion, at least the f of I plus 1 minus f of I divided by delta x. So there also there will be some amount of truncation error which will come in even in finite volume method. Although we can maybe argue that it might be less, because if you are directly doing in a PD, you will be applying the Taylor series for this, and as compared here, it will be, you can make it very easily a second order. Here it might be a first order. You can maybe improve that, but the truncation error will be there, I think. Higher accuracy, yeah, higher accuracy you can say. uh, yeah, but the main thing is, apart from this physical intuition, that even for a conservation equation which does not have a partial differential format, even for that you can come up with a kind of linear algebraic equation. That is one thing. The second thing which is very important to note here is that the finite difference method can be kind of be applied very easily to simple geometries. Yeah, one of you have already pointed it out, FVM suitable for complex geometries. For complex geometries, when you try to go with a finite difference method, okay, you cannot directly apply it. So for example, say some geometry is something like this, okay, so it is a curved tube, okay, this is the inlet and this is the outlet, okay. You cannot directly apply df by dx as f of I plus 1 minus f of I divided by delta x here. So you will be generating something known as curvilinear grid, okay. Okay, so you will be generating something known as curvilinear grid for this type of problem which is shown here. Okay, now you can indirectly use finite difference method for this geometry. Okay, so for example, you have df by dx plus df by dy is equal to 0. Okay, now you cannot directly write dfy by dx for this particular geometry. Okay, so first of all, that is not possible. Uh, because you do not have a straight grid here to write to df by dx. But again, there is something called as Jacobian transformation, which is, I don't think, which is there in this course contents also. You can convert this in terms of computational space. This whole grid you can convert into a rectangle. Okay, the whole equation will get converted. Then the equation will not look like this. It will be something like dou f by dou zeta. Zeta and eta are like the computational coordinates. We uniform like with this simple geometry, we try to convert this. Okay, and then the equation will get modified. This dou f by dou eta will also come. Okay, and then we get dou f by dou zeta dou eta also, the mixed derivative. So equation will change, and then we can again apply finite difference method. But the thing is, these are very much complex, and especially when we come up with a non-linear equation, we cannot go with that kind of transformations. Okay, so when the equation is highly non-linear. So for complex geometry problems, it becomes very difficult to kind of apply finite difference. My screen is not visible. I am writing something on paint. Is it visible? Just let me check, because I am writing on paint. Okay, okay, it is visible, right? Okay, okay, fine. Thank you. Okay, okay. Because I am writing on the paint here. Okay, so this curved tube and all that should be visible. Okay. So yeah, what I was saying. So these equations will get changed. So you cannot, and if it is non-linear equation, you cannot directly apply. Okay. I mean, for simple nonlinear it is possible. Again, if we have say u square into dou u by dou x or something like that in some transport equation, just you cannot convert this in using the Jacobian transformation and all. Okay, so it is very difficult for complex geometry problem. And especially in some see, this curvilinear grid is also a again a highly debated thing and a highly discussed thing. Okay, uh, this curvilinear grid, again, you can kind of generate for very this simple cases. Again, this is a curved tube or something like that. Say if you have again kind of um, say very complex geometry, okay, which is like this, something like this. Okay, now given if you want to generate a grid around this particular geometry, So this is basically a cylinder, a wrapped cylinder, something warped cylinder. Sorry. So you cannot generate a particular grid for this curvilinear grid. Okay, it becomes very difficult to generate a curvilinear grid. Here there will be too much of, say, uh, deformation of the grid. It becomes very skew here. So for example, if you have, again, instead of this warp cylinder, we can consider cylinders which are in tandem arrangement, that is very closely placed. Okay, and if you have flow over this. Okay, now here if there are single cylinder, again you could have kind of uh, generated a curvilinear grid. But here in between these two spaces, it becomes very difficult to generate this curvilinear grid also. So you cannot, first of all, you have to go for an unstructured, say, triangular mesh and all, or else you can also use immersed boundary method, again, which is a separate topic altogether. Okay, uh, but you cannot kind of directly implement a finite difference. Okay, so these are the two advantages of using finite volume method over finite difference method. Okay, is this clear? Any queries regarding this? Because this has to be very clear, why we, because finite difference is very easy to do. Okay, finite volume you will have to do some homework. Finite volume, because you have to understand that. Okay. Okay, so if that is clear, so let us go to the next point. And finite element is uh, actually a more accurate method, uh, and mainly we use it when we kind of go with a highly nonlinear equations, which are very susceptible to errors when we use finite volume method. But that was not much discussed in the weekly content also, and you don't have much questions on that. Okay. And mainly it is dealt in solid mechanics. In typical computational fluid dynamics, we use finite volume method. I mean, there are people who use finite element also, especially for hypersonic flows and all. But mainly we use finite volume method in CFD. Whereas if you go to computational structure dynamics, CSD, so there we use finite element method. Okay. Now coming to the different schemes. Okay. So as I said, the basic of the equation, what we see is a diffusion equation always, whenever we are starting with some new topic. Okay, so if we consider a transient diffusion equation. Okay, so mainly, for example, say there is a rod like this. Okay, wherein the temperature is varying only in x direction. Okay, so this end is maintained at 0, or it is exposed to air, or whatever you can say, it has some specified heat flux, and this is maintained at 100 degree. So how will the temperature vary over this particular region? So that we try to analyze it using the diffusion equation. Sorry, should be dou square t, not u, dou square t by dou x square is equal to 0. Okay, but in reality, see this, when you take a rod and then heat one instantaneously kind of subject this to 100 degrees Celsius, and instantaneously subject the other end to 0 temperature. Okay, then definitely it will not immediately come to an equilibrium, right? So it will slowly, the temperature will slowly move, the heat will slowly move from left to right hand. So there is always a time which is involved in reality. Okay, in reality, in CFD you can just solve this by equating to 0, but that is not a kind of realistic thing to do. Okay, so we always try to solve it in a transient manner. So we have dou T by dou T. Okay, with respect to time, how the temperature is varying is equal to alpha. This is the thermal diffusivity. Okay. So whenever you are starting with CFD, I mean, when I took the introduction, many of you said that you were kind of new to CFD and you have not had a coding experience with respect to CFD. Okay, so assuming that the audience doesn't have a background in CFD coding, the best thing to do would be to start with a transient equation. Okay, so this might seem counterintuitive, but actually when you start with a career, or you want to focus your studies in CFD, if you want to go ahead in this field, it's always the better thing, it's a better thing to start with the transient equations. Okay, although it might seem difficult as compared to writing d square t by dx square is equal to 0, writing this you might feel that it's a bit lengthier, but actually you will see that writing a code for this is much easier than just writing a code for dou square t by dou x square is equal to 0. I will just show it why using live code. Okay, for this equation we will try to write a code today, okay, in MATLAB, and then just try to see which of the schemes is better. Okay, am I audible? Is my voice coming clear? Because sometimes my microphone will just can you write down on the chat box? Okay, okay, thank you. So yeah, so we will write the code for this particular equation, how to solve this equation. uh, Always I feel that practical experience in any subject will enhance the learning. So I mainly will focus more on this coding aspects as and when the time passes. Okay, as and when we go to next week's content and in this week also. Okay, so if you are uh, learning that thing, the other theory thing you will quite pick it up quite easily. I don't think there should be any problem, and then it the subject also becomes somewhat interesting. So what I was saying is that starting with this particular type of equation, the transient equation, is more easier. Okay, so we will try to start with this. So when we kind of start with these equations, we have two choices. Okay, so it's like we are marching in space and we are marching in time. This is the space coordinates. Although here only there is one coordinate, you can have two also, d square t by dy square also. And then we are marching in time also. So it is like space time coordinates. Okay, so you have space x y. Okay, here only we have x, but assume that there was y also. Okay, so this is our x y coordinates. Okay, this is x and y coordinate. Now we have another coordinate which is our time coordinate. Okay, this is at t is equal to 0. This is at t is equal to some time step, say delta t. At delta t we have another set of values of variables. Okay, so here you might have one temperature t1, here you might have another temperature t2 at the same point. Okay, so this is marching in time, and within this you are marching in space. So there are two loops, one is the space loop, and the other thing is the time loop. Okay. Okay, there is a question. Is there any course available which teach about CFD coding? In NPTEL, I have not seen much. Okay, I don't know, but um hmm, there is some course on Coursera. Maybe you can look through that. CFD, some practical coding or something. I don't remember. I had seen it very long ago. I will just let you know next week maybe. Okay. But the main thing is you can just search on YouTube only some coding for some diffusion equation, coding for lid driven cavity problem and all. You will get many videos. Okay. So that is also one way in which you can start coding. And there is one book, Numerical Recipes in C. Okay, that's a very general book. It's not a CFD book. Numerical recipe this is for C language. Okay, and there are books for C++, everything. Okay, numerical recipes in C++. So basically, they explain in that book how do you solve a general diffusion equation, how do you implement Gauss Seidel solver and all those things. Okay, so the algorithms, everything are given quite clearly, but they do not focus on CFD. Okay, they just take a random variable f, dou square f by dou x square is equal to 0. How do you solve this? Okay, so these things are there in that particular book. Okay, but in general you will get many YouTube videos, but I don't know whether there is a some course which only deals with coding. Okay, so I am not really sure about that. Okay, so yeah, so this is the time coordinate. Okay, this is space coordinate, and then we go into from one time to other time. Okay, now you have some variables in this time. Okay, some temperature value, 2 degree, 3 degree, something. Okay, in this particular time t is equal to 0. Now uh, and you want to calculate the variable, the temperature value, at a new time step. Okay, when you march. Okay, t is equal to delta t. Now you can have two options. Actually, there are three options, but let me just restrict to two options. First, okay, you can use the variables, the temperature values which were there at this space. Okay, at this time instant t is equal to 0. Otherwise, you can use the values of temperature which are there in this, which you don't know. Okay, which you are trying to calculate, but you can still use them and make them a system of equation and then try to solve them using the Gauss-Seidel method or something like that. Okay, so that also you can do. So there are two options. Okay, and you can argue definitely that the second option is much more accurate, or it will be better or something like that, which we feel intuitively. Okay, we want to calculate the variables over this time, and for this diffusion part, dou square t by dou x square, this is the main part. So in the space, which temperatures do you want to use already at the t is equal to delta t, the temperature values, or the temperature values at the older values, older time. Okay, so you might say at the new time step only we will use for d square t by dt dx square. Dt by dt is anyway clear, we will go from n plus 1 to n. So usually this is called n plus 1 and this is called n. Okay, so this is called n. That is quite a clear thing, but the question comes here: d square t by dx square. uh, so how do you go about that? The first option is you will use the older values. Okay, older time, and the second option is you use at the newer time instant. So I would ask one simple question: which option would be more easy with respect to coding, with respect, just purely with respect to code? Which option would be more easy? The first option wherein you use the previous time step temperature values, or the second option wherein you use the new time step temperature values? Which option would be easy? Can you write down on the chat box? Previous time step, yeah. So obviously when you write a code, uh, you do not know the temperature values at this time step already, right? So if you use that, you will come up with a set of linear algebraic equations which you have to solve simultaneously to get the result. That is a quite tedious task, whereas if you are using this, it becomes very easy. Okay, and this is where we start in CFD, and this is called explicit time marching. Okay, wherein we are using the temperature values or the flow variables at the previous time step for our space coordinates. Okay, when we want to discretize the space coordinates, dou square t by dou x square, we use the values at the previous time step, previous time level. Okay, so that is particularly the explicit time matching. Now the opposite, if we are using at n plus 1 only, that is called implicit time matching. There is also a third scheme which is called as Crank-Nicholson scheme, which I will not discuss much, but we use an average of both the things. Okay, it's kind of thing. So that is also possible. Okay, so in general, so let me write dou t by dou t. Again, here we have something called as forward time. So we use t at n plus 1 minus tn divided by delta t. Now dou square t by dou x square. Now I want to write it using uh, explicit time marching I am using. Okay, so I will write it with respect to t at n only. Okay, to whatever n time step is there. But here we again kind of uh, come with options. We can use a forward difference scheme, backward difference scheme, or a central difference scheme. Last week I had already discussed this. Can you write down on the chat box which of the schemes will give a much better accuracy? A forward difference, backward difference, or central difference? Given a set of equal stencils, so I can use only I plus 1, I and I minus 1. Okay, only I can use 3 points. Which scheme will give me more accuracy? Yeah, central, yes, exactly. So central difference will give me more accuracy. Okay, so I'll just write down using central difference ti plus 1 minus 2 ti plus ti minus 1. Okay, divided by delta x square. Meanwhile, whenever I am discussing, if you have any queries, you can just write down on the chat box also. Okay, I'm monitoring that also, and if you have any queries, I'll just interrupt. I'll just stop and then clear your queries. Okay, so d square t by dx square, you write it like this, and dou t by dou t you have already written it like this. So this is how we write the code. Okay, it becomes very easy now. You can see t at I at n plus 1 will now be equal to t at I at n plus alpha delta t by delta x square into again d square t by dx square, okay, which we have already written it here. Okay, and these are all at nth time step, so only direct you can calculate ti n plus 1. This is very simple, right? I mean, if there were only 2-3 points, you could have done this on a book also, in a same using simple pen and paper calculation. We can write a very simple code for this. Okay, it's very easy. So that is why I would suggest whenever you are starting with coding, start with explicit time stepping for any kind of equations. Okay, these will also work given these have stability problems that you need to have very small delta t. Okay, but these will give you good results. Okay, so always start with this. This is the basic point. Then you can go to implicit. There the things become a little complicated. Okay. So yeah, so this is what the explicit versus implicit, and I also explained FT, CS, FT, FS, forward time, forward space, central space, backward space, and all. Okay, uh, and then errors also you kind of studied. Okay, now what are the different types of errors which you can come up? You have like the truncation error, which is already there. I think the second thing is the round off error. Okay, round off error, your computer will have only set of fixed decimals, and then when you are solving micro scale flows wherein the values itself, the normal values are itself in 10 raised to minus 6, u is equal to 10 raised to minus 6 is there, it will store it as 0.00001, whatever, 0.0000001. Okay, then you, if you have some variation in that value, 1.123 into 10 raised to minus 6, those things will be lost. Okay, because of the round off error. So one strategy is to avoid this round of error is non-dimensionalization. When you non-dimensionalize this with a characteristic scale velocity, that itself might be 10 raised to minus 6. So this 10 raised to minus 6 divided by 10 raised to minus 6, you will get 1. Okay, so now you will not have much round of errors. Okay, when you are using a dimensional code, you might land up with round of errors, and I have seen people struggling with this round of errors also. Okay, the solution does just goes like very big. I mean, because of round of errors only, it is very tricky thing. And whenever you are using ANSYS, let me tell you, it uses a dimensional code. Okay, it doesn't do non-dimensionalization and all, and many a times you use single precision. I know when you open the Fluent, you will use single precision. It will take only 8 decimal places, and if your scale, if your dimension itself are very small, then the velocities will be small, all the round of errors will come in, and the solution will diverge. So in those cases you have to use at least double precision, you get 16 decimal points. Okay, in the computer. So that is a very big error. I mean, it's not taken very serious, but I have seen people struggling with it. Okay, So please be careful with round off error also. Truncation error you already know. Last week we have discussed what is the maximum order which we can get when we ignore the leading order terms. Okay, so the first thing which we get in the leading order term, the delta x square, delta x cube, whatever it is there, that is the order of accuracy. We are ignoring those terms, so we kind of end up with truncation error. Okay, and one of you had asked a question. I think can it be a decimal, the truncation error? No, that cannot be a decimal values. I had told it also, but I was not 100% sure. But I did some research. Okay, so again, I am confirming that it cannot be a decimal place, the truncation error. Especially if when you are using the Taylor series finite difference and all, it cannot be a decimal place. It is a decimal place during your spectral methods and all, which is a different topic. But here it is not. The order of accuracy is not in decimal; it is a integer. Okay, and then you also have discretization error, as you already rightly mentioned. With finite volume, finite difference, we kind of end up with different results. Okay, so that is the discretization error. And that is the error analysis which you had written in the chat box also. Now a very important thing which I already told you, I think, is the analysis of the discretized linear equations. Okay, so that is very important. So just hold on. Yeah, so analysis, you write some code, okay, it will not converge. Now you kind of uh, think here and there, you check the code, you never will you get the correct answer from the code, because you are implementing a wrong scheme. Okay, your code is correct, your logic is correct, okay, but the implementation scheme itself is wrong. Okay, so that is why you have to analyze a numerical scheme. In analysis you come up with a consistency, okay, and you come up with what is called as stability. Yeah, that is very important. Consistency and all, that is fine, okay, but what is more important is stability. Okay, I will give more importance to that. Okay, because with respect to time, the errors might get accumulated in a scheme, and that might lead to your value of the flow variable at say and n plus 1 becoming very large. Okay, as compared to u at n. So for this, so typically what you see is when you are giving an unstable thing, you will get some values, but they will be like in 10 raised to 10 or something, 10 raised to 20 something. Uh, that is mainly the stability issue you have to understand in your code. You have to always debug the code from different point of views. Okay, whenever you want to debug a code, it's not just that you see the code and just see whether it is correct or not, the logic is correct or not. That is just one part. The other part is the analyzing your scheme itself, what you have implemented. So that is very important. Okay, so uh, you have to do something called as von Neumann stability analysis for a scheme, which you might have already seen in the week 3 contents. Okay, so what is the main assumption when you do a von Neumann stability analysis? Can you write down on the chat box? How do we approximate a particular flow variable in von Neumann stability analysis when we want to do? Can you write on the chart box? I mean, the main assumption which we take in the von Neumann stability analysis, we take the initial variable u of n as some approximation. Can you write on the chat box? Yeah, so this thing is a very important thing, von Neumann stability analysis, and many people kind of ignore it. Okay, but I will tell why. Okay, no problem. I'll just tell it. Okay, so we mainly express this as some periodic function. Okay, so you know that I mean, you might have already seen that any kind of curve, any kind of variation over time. Okay, so this might be any variation. So it will look something like this, right? It will be some smooth curve, assuming it will look something like this, right? So how can you approximate this using an equation? Which equation will you use to approximate this curve? Can you write down at least that on the chat box? So I have a curve something like this. Okay, this is my solution. Assuming this is the solution, how do you approximate this solution? Which equation will you fit? Okay, equation fitting that you might know. Polynomial, yeah, you can put a polynomial, but polynomial is always not a good option. There is something which gives more better result than a polynomial. Okay, polynomial, because if the curve is like this, you have to go with many polynomials like ax square, ax cube, ax raised to 4 5 degrees will be very high. You cannot just settle with ax cube or something like that. It will be very difficult. Okay, yeah, Fourier. Yeah, so basically we as rightly mentioned, we use a combination of sine and cos. Okay, uh, we use a combination of sine and cos to fit this type of curve, any solution. Okay, so that is the main assumption, that this variable follows a sine cos trajectory. It can be expressed as a combination of that, and so then we express this as something like e raised to I theta. Okay, e raised to I theta is sine theta plus I cos theta. Yeah, you already know that. Okay, I theta into that at the grid point at I. Okay, now I have this I. Theta again depends on the your what do you say, the delta x value, the difference between the two grid points, the distance between the two grid points. Okay, so this is the expression which we use. Okay, then we try to substitute this u at n plus 1 also you can calculate similarly. Okay, now you can substitute this in this your governing equation and check how u at I at n plus 1 divided by u at n, ui at n, will this be greater than 1, less than 1? Okay, what will it be? So if it is greater than 1, it means that the solution is diverging. Okay, I mean it's the magnitudes are increasing. Okay, over a period of time. Okay, so, and this I am talking about capital U, huh? This is capital U. So the amplitude is increasing. So basically, if something there is something like this, so you can say this is capital U of n. Now if you are getting something like this at the next time step or something like that, it is increasing, which will continuously grow and increase, and then it might land you up in trouble. Okay, so that is why we try to ignore such situation where it is going greater than 1. We try to avoid such situations. Okay, uh, that you have already learned in week 3 contents. Okay, so hopefully that was the contents which were mainly there. Are there any queries regarding this, or shall we go ahead with the questions? I will just discuss 3 to 4 important questions and then write a code. Okay, simple code. uh, that is the main thing which I want to do today. I think it's already nearing 7 o'clock, so I'll just discuss some questions. If there are any questions, please post them on the chat box. Okay. So here is the question number 1. Choose the correct statement with respect to the following figures. You have two pictures which correspond to two way of generating the grid control volume in finite volume method. Okay, so these two corresponds to two different methods. So can you tell me what is picture 1? Which method does it correspond to? Picture 1. Can you write down on the chat box? Yeah, node based. Yes, node centered. Yes, correct. Hmm. So, picture 1 corresponds to the node centered control volume generation. Okay. So, why it is called node centered? Basically, first you generate this cell. Okay, you give an equation. Okay, you kind of, for example, if you have a rectangular domain, which have I think explained it here. Okay, first you kind of do this lines create those lines first. Okay, the corners first, that is what I have done, and then take the centroid and then create it as a node. Okay, so that is the centroid as a node is created next. Okay, as a it is created as a centroid, the node is created as centroid, so node is centered here. Okay, so that is why this is node centered, node is at the center, whereas in the second thing the cell is at the center. Okay, so basically these nodes are generated first. I mean it's the same thing, but it's just that we call these as nodes instead of calling them as corners. Okay, and then we generate the cell around this node, so that the cell becomes at the center, cell comes at the center. So this is quite a bit a difficult thing to do, and usually I have seen node centered, which is mainly used in the finite volume method. Okay, so that which should be the correct answer then? Yeah, I think I have already written it here. Okay, the nodal in the picture one, which is a node center, nodal value is the mean over the control volume. Okay, okay, so the first option is not correct. That is why I told you. Okay, usually node centered is used. That is picture one is usually used. Okay, in general finite volume method also, because that is kind of intuitive also, and that is not difficult also to do that. Okay, you just generate a grid, then you just calculate the centroid. You know how to calculate the centroid, and then you assign this as a node. Okay, then you do the calculation. Okay, so that is quite easy. Okay, then let us come to the second question. If u of I at n plus 1 time step is equal to u at I grid point at n time step, so this is I think for a 1D diffusion equation which we have discussed till now. Okay, 1 hour we are discussing this only. Okay, plus r into this whatever is there is an explicit way of expressing. So is this true or false? I mean, everyone should answer this because till now we were discussing this only. What about others? Can you all also answer? I think we have discussed this. Okay. So they are telling that this is a explicit way of expressing. So, so this is the expression. Okay. And I think most of you have written it down already that true is the correct answer. Yes, true is the correct answer, but we will see why again. So using the forward time and central space, we can write this dou u by dou t for a diffusion equation as u at I n plus 1 minus u of I divided by delta t, and again this dou square u by dou I square using the central difference scheme which I already told. Okay, now you can see that we have n time level. Okay, time level is n here, it's not n plus 1, so it's an explicit treatment. If I would have, if I wrote n plus 1 here, that would have been your implicit treatment. Okay, so since there is only n time level, okay, it is an explicit treatment, and so the option should be correct. Okay, I hope this is understood. Okay, if there are any queries, just write down on the chat box. Okay, so question number 3, the error formed due to neglecting the leading terms is called, what is it called? We have already discussed this in last week also. uh, Maybe I went 1 week ahead. Okay, one of you have asked in week 3 assignment. There is first question: which of the following describes the usage of FTCS scheme while solving 1D understudy heat conduction without heat generation? No, no, I don't know because see, I don't know. I don't have. I don't. I have not seen the week 3 assignments. I mean, but what I don't know what are the options also. Okay, what should we answer, a implicit or explicit? So you can use both, a implicit or explicit. Okay, see in central space it is not mentioned explicit or implicit, right? So central space can be implicit or explicit both. Okay, so I don't know, it depends on the options. I think I have not gone through those your actual assignment questions because we are not supposed to go through them. Okay, we are not supposed to solve the actual week's contents questions. Okay, but I can give you a hint. As far as I can understand, which of the following describes the usage of FTCS scheme? I think it will depend on the options. What are the options which are available? Uh, I think both we can use explicit and implicit in a FTCS scheme. Okay, because it is forward time central space. Now in central space you can also use explicit or you can also use implicit. So that is what I was discussing. Okay, so I don't know. So whatever you have asked based on that. Okay. So, okay, discretization error. Okay, so that is what we were discussing in the beginning of the class, right? And I think one of you also wrote that the finite volume method is much more accurate than finite difference method. So that is where the discretization error comes. So when you are using different discretization schemes, you are landing up with different results which are again different from the analytical results. But the finite volume method might have a much more accurate result, might land you up with a much more accurate result as compared to a finite difference method. That is the discretization error. Now finite element method, if you go, you can come up with much more accuracy, but it is a difficult to implement scheme. Okay, now why do you get that? Okay, so that also we tried to see, I think, during the discussion, that you just, if you have dou square u by dou x square, okay, and now if you have only say two stencils, okay, you will be using three stencils for this. Okay, and for example, if you see a forward difference scheme, if you are using three stencils, you will get up with first order accuracy. Okay, with those three same stencils I can come up with a second order accuracy in a finite volume method, because I am doing the integral and then I come up with dou u by dou x at east minus west. Okay, so with the same thing I come up with a more better accuracy. And one more thing which you have to do is, when we write this dou u by dou x and expand this, we usually land up with less error as compared to discretizing this dou square u by dou x square. Okay, so that is why we have different accuracies with different discretization schemes. Does that answer your question, Ravi Karan? Okay, thank you. Okay, yeah, so this is the truncation error, which is formed due to neglecting the leading terms. Okay, so whenever we write this expression f dash of x, like for example f of x minus f of x plus x minus f of x divided by delta x, we ignore these terms, right? Delta x square, delta x cube, and all. We ignore those terms. Those are the neglecting the leading terms. So this is usually called as truncation error. Okay. Let us see fourth question. Again, this is based on whatever we have discussed now. Okay, so the dou t by dou t is equal to alpha d square t by dx square equation is discretized with FTCS, and the discretized equation is given as so and so. What should be the terms p and q? Can you write the answer on the chat box? It is the central space. Okay, so it's the central difference they are using here. What should be p and q? I think q is very easy. Q should be delta x square, because we have delta x square here. Okay, that is very easy. It cannot be delta x, I mean. What should be p? Can you write down on the chat box? Okay, Ravi Karan, you are asking, you are not able to differentiate between the truncation error and the discretization error. See, that is what I am telling. See, for example, here, if you are, this is the truncation error. Okay, this is due to the leading term error. Okay, but if you are using a different discretization scheme itself, the truncation error will reduce. Okay, So that is why you get a results with by using the same stencil size, you get different accuracy in the results. Okay, ultimately that is because of truncation error only. What you are trying to, I can understand what you are trying to express. Okay, ultimately it is because of truncation error, because you are finally coming up with a scheme which with a given stencil will have less truncation error, and because of that only it will have less error. But the main thing is that you are using a same difference scheme, you are using the same difference scheme. Okay, for dou f by dou x, say forward space, there also you are using forward space only for dou square t by dou x square, everything remaining the same. The only difference in error is coming because of your discretization methodology. Okay, so that is why it is a discretization error. But again I would say, below that, when you kind of go down, you will see that change in discretization error is because of change in truncation error only. But you are using same scheme. Okay, it's like, if I was say f dash of x, if I was using a central space instead of this forward space, I would come up with delta x square. So then the truncation error would change. So that is the definition of truncation error, that is the leading term which comes here. Okay, so that is the truncation error. It is a one set of error. Now when you go with a different discretization scheme, you will end up with that, with using the same stencil you will get a better accuracy when, for example, when you are using finite volume method, because of change in truncation error. But the thing is, you have changed the discretization scheme, that is why you are getting a lower truncation error. So does that answer at least now the question? So if you go at the lowest level, the difference comes in because of truncation error, but actually you are using different discretization scheme, and that is why you kind of get different results. Okay, the definition of truncation error is this. Okay, only this. Now I'm not discussing anything about the discretization scheme when I'm discussing about truncation error. Okay, and one more thing which is coming to my mind as of now is that, see, when you go for a complex geometry problem, and when you go for a finite difference versus a finite volume, finite difference you kind of convert it, you do a Jacobian transformation, and the Jacobian transformation also has some error. So what it will happen is that there the error will again get added up because of Jacobian, apart from the truncation error. Okay, when you try to approximate that equation, so there also there is a different discretization error. It's not only with respect to truncation error. Okay, so that is why the discretization error, it is like a I mean altogether combined one particular error, that is discretization error. Okay, yeah, I hope it is clear. Okay, and this, yeah, p is equal to minus 2, many of you have already pointed it out. Okay, the central difference scheme, we come up with t at I plus 1 minus 2 ti, so minus 2 will come here. Okay, so yeah, so let me see whether I have some important question. So as you can skip this. Yeah, Dufort-Frankel I want to discuss. Okay, this is an important thing. Okay, uh, in Dufort-Frankel scheme, okay, this is uh, a a modification of the forward time central space. Okay, uh, but yeah, I think I have told the answer already. So it is actually a forward time and central space scheme, but you are doing modification in that forward time and central space scheme. Now what modification are you doing? Okay, in the forward time central space scheme, that you are, instead of you I at n, you are taking u I at n minus 1. Okay, and in the spatial coordinate you are taking u I at n, you will end up with u I at n. Okay, here you are taking it as average. Okay, average of u at I at n plus 1 n minus 1 by 2. So just let me make it clear by doing the diagram here again. So you have three time levels. Okay, So you have three time levels corresponding to these three slabs. Okay, you have n plus 1, you have n, you have n minus 1. Okay, now you can usually what do you do in forward time central space is you go from this nth time to n plus 1. Okay, now in this Dufort-Frankel scheme we try to improve the stability of the scheme. We will see how it improves. I will give a physical intuition also, although von Neumann stability analysis you have done and seen that it is a unconditionally stable scheme. Okay, so you try to go from n plus 1, you try to go from n minus 1 to n plus 1. Okay, you use the values of n minus 1 for the time. Okay, for dou t by dou t. Okay, at n plus 1 minus n minus 1 you use, and when you go into the space and when you want say at I comma j in the central space, you come up with t at I plus 1 minus 2 ti and ti minus 1 also, right? So ti minus 1 and ti plus 1 we take it from this nth only, as usual. But this ti what is there at n, ti at n, again we do this as an average of these two time steps. Okay, at n plus 1 and n minus 1. Just understand the scheme now. I will tell why we are doing this, all these things. Okay, so that is how I have written here u at I at n plus 1 plus u at I at n minus 1 divided by 2. So that is what we do here. Okay, and then it is a forward time central space, that is true. It is a modification of that. Okay, so the answer should be forward time central space. Now, similar related to this is the next question actually. The Drufford's Frankel scheme, if you do the von Neumann stability analysis, which I explained it, okay, to you all just some time ago, how do you do that von Neumann stability analysis? So when you do that stability analysis, you see that this particular scheme is unconditionally stable. That is, what will happen is, what is meant by unconditionally stable is this u at n plus 1 divided by u of n, which I was discussing, given any conditions, given any delta t values, because ultimately I think in this expression you will end up with f of alpha delta t by delta x square. I think this is a function of alpha delta t by delta x square. Okay, so given any delta t value, always this is less than 1. Okay, for a Dufort-Frankel scheme. So that is why you say that it is unconditionally stable. Okay, that is the main reason. It is always less than 1 given whatever delta t value you select. Okay, why? That is the question. No, mathematically we saw why. Okay, we implemented this scheme, we did von Neumann stability analysis, which you can do very easily. Okay, that's already given in the notes also. Okay, you can do and check that it is less than 1. But always I feel that apart from dealing with the things in a mathematical way, a physical intuition will give a more beauty to the scheme. Okay, so always you need to have some physical intuition of what is going behind. Okay, mathematically you can prove it. Okay, but physically, I mean intuitively, how do you understand this thing? Okay, so see, let us for example take a solution, okay, which is very kind of wiggly in time, with respect to time. Okay, so for example I have a value of u which is varying like this. U I always go with just correct me. Okay, t or u whatever it is something, it is going with respect to time, something like this. Okay, it is too much wiggling, zigzag nature. Okay, now if I take say t plus 1, I sorry n plus 1. Okay, n at n minus 1. Now for this type of cases, if you see, if I interpolate with n, okay, I might land up with somewhere here, direct interpolation. Whereas if I take from n minus 1, I will come like this. Okay, so always you with this Dufort-Frankel scheme, you will get a smoothened solution. Okay, you will get a smoothened solution, which might not be very accurate, but it is very stable. Okay, you will not land up with this wiggle. So what will happen if you use FTCS directly is that you will come like this, something like this, and ultimately it might diverge, the solution might diverge. Okay, these things are it might happen, okay, with the normal FTCS scheme. Okay, so when you use Dufour's Frankel, it kind of smoothens out the solution. Okay, is that physical intuition understood? I mean, did you understand that? I mean, because that is very important. I mean, whenever you try to analyze a scheme, try to analyze it like this also. Okay, this will give direct understanding. Okay, it is kind of doing an averaging here. It will smoothen out. It will skip this n because we are using t at n plus 1 minus t at n minus 1. Okay, and at I comma j also, that is why we did the averaging. T I plus 1 and I minus 1 I did not do, only at t at I comma j I did this averaging over the n plus 1 and n minus 1. Okay, is this understood why Dufour Frankel is an unconditionally stable, I mean, with this graph, not with a von Neumann stability analysis? Okay, okay, thank you. So that was the question. Okay, and here I have given the answer with respect to mathematical analysis. Okay, you can do mathematical analysis everywhere and okay, and come up with answer. That is the one best way. But also to understand, we need to have physical intuition. Okay, so yeah, so these were the questions which I wanted to mainly discuss today. Okay, so I hope things are clear now. So main thing which I want to do this week is start with coding, and this coding exercises, sorry, the coding exercises we will be doing every week from now. Okay, because one of the important thing in CFD is C, that is computational. Okay, so you have to do something computational, that is coding. Okay, because only if you are learning these things, I don't know how much useful it will be. So in typical class setup, I mean, I know it is very difficult in NPTEL. In a typical CFD class setup, wherever I have learned CFD, we always, I think my laptop is slowing down because MATLAB, MATLAB started. Okay, so in a typical class, we always have coding assignments. Okay, coding assignments, coding projects, always in a CFD class. Okay, so that is the way in which we have learned. Okay, uh, I particularly feel that whenever we do this, our theory also becomes strong. Okay, so that is why I'll just do a small exercise. Okay, just pardon me because my laptop is becoming slow or what, I don't know, because I have opened two MATLABs. Okay. Yeah, I had suggested this in the first class that it would be good if you can install MATLAB, or else now you have MATLAB online. You just need to create an account, sign up. Okay, you can use it online also. Okay, you need not install the software. Okay, and I think they do give us a student version or something like that. You can use it. I mean, there is one more software which is a open source, freely available. It is Scilab. Okay, it is very much similar to your MATLAB. All the functionalities are there. Okay, you can use that also, and the syntax is also same. Okay, in Scilab. Uh, okay, so you can use Scilab also, but MATLAB also you can use it online. Okay, online MATLAB you can just directly use it. It's taking some time to open, I think. Okay, in the meantime, if you have any queries regarding this weekly content, you can discuss. Okay, we will just solve this equation, this diffusion equation. Okay, just let me give a brief background before solving. Okay, I just don't want to directly get into code. Okay, so you have, as I said earlier, uh, a rod which is subjected to 100 degree at left end and 10 0 degree at right end, and you want to see the variation of temperature along this rod. It's an x directional. The temperature variation happens only in x direction. Okay, um, so that is the problem statement. Now what do you do? First step, can you write down on the chat box, what do you do? What is the first step here? what do I need to do with this domain? This is my 1D domain. What do I need to do? What is the first step? Okay, so the equation is dou t by dou t is equal to alpha into delta square t by delta x square. Okay, this is the equation. What is the first step in CFD? We will try to revise all the week's content now. Okay, what is the first step? Discretize. Yes. So we have selected the domain. That is also one particular important thing in CFD. First thing is to select the domain where we want to study. Okay, again the first step, again the first sub step is to discretize, that is the pre-processing. I would say, I would not say discretization, I would say grid generation or domain division. Okay, discretization is again how do you discretize this equation. Okay, let us come to that in the next part. Okay, I will just say domain division or grid generation. Okay, now here it's a simple thing. Let me just divide it into some uniform elements, say 10 elements I will divide. Okay, so the total number of grid points, so I am using finite difference method, simple thing. 1 to 11 it will be. Okay, I am dividing into 10 parts. Okay, so delta x will be L divided by 10. So L say 1 meter. Okay, so 1 divided by 10. So that is the domain division or grid generation. Now the second part, as you said, is discretization. We have to convert these. Let me close this one window. Okay, so converting this algebra partial differential equations into linear algebraic equations, which we have discussed for 1 hour today. Okay, so let me just not go into details about that. So Ti at n plus 1 minus Ti at n divided by delta t is equal to alpha into Ti. Okay, alpha delta t by delta x square it will come. Okay, I will write it as d. I think in your notes also it is there as d only. Minus 2 ti. Okay, I'll just remove this also. Sorry. D is nothing but alpha into delta t by delta x square. Okay, plus ti minus 1. At nth time step, I am using an explicit time stepping, very comfortable for beginners. Okay, Ti at n plus 1 is equal to Ti plus d into this thing will come in. Okay, so this is the code. This is, I mean, I will write the code, but this is the whole thing. Okay, so just let me write from scratch. Okay, so L is equal to some 1 units. Okay, so if you are having MATLAB installed, you can open it and write the code along with me also. Okay, so let me take n is equal to 11 points as I said earlier. Now after doing this, you need to calculate what is delta x. Okay, delta x will be nothing but what will it be? L divided by n minus 1. Okay, I can all change this at any moment. Okay, so that is why I write general L is equal to n is equal to so and so. One more thing which I have to define is delta t. Okay, that is also very important. I am solving a transient equation, right? Now, what is d? Alpha. So alpha into delta t by delta x square, right? Into delta t divided by del x or del x. Okay, this is the pre-processing things which I have to do. Okay, what are the other things which I have to do before going to time marching? I have to define the variables, right? So let me write t old. Okay, and what do I need? I need t new, that is n plus 1. T old is tn. I also need t old of old, that is n minus 1 also I need, right? So these are three variables which I need. T old of old is n minus 1. Okay, now I'll write it as just zeros of say n comma 1, one dimensional array. Okay, T old is the same. Just let me copy paste this zeros. Okay, now I have done this. Initial conditions I have to give for all these variables. Okay, so just let me start with t old of old. Initial conditions. Okay, t old of old. So as I explained in this problem, it is 100 and it is at 0. Okay, it is an initial condition as well as boundary condition also, you can say. Okay, t old of 1 is my 100. t old of n, that is the last grid point, is 0, right? So that is the initial as well as boundary condition for my case. Okay, now t old I have to define and t new I have to define. I'll just write it as t old of old only, same, take it same. T new is equal to t old, whatever it is. Okay, now I can start with the time marching. Okay, so initially time is 0. Tm I have written, it's just a shortcut. So I'll write while time is less than say 10, because I am doing a transient equation. I have to stop at some time. I'll tell there is another way how we can stop, but this is for easy understanding. Say I'll just fix it 10 seconds. Okay, while time is less than 10 seconds, this is the time marching. Okay, now time marching, I'll go tm is equal to tm plus delta t. I am marching in time now. Okay, now what is the next thing I have to do here? Apart from time marching, what is one more thing? I told that there are two marchings which we have to do. One is time. The what is the other marching? Can you write down on the chat box? Yeah, space marching. Yes, very good. So for space marching, I would use the for loop. For I is equal to 2 to n minus 1. Why I am using 2 to n minus 1? 1 is my border and n is also my border. Okay, I am not calculating anything on the border because I have border conditions, boundary conditions. Okay, so only 2 is 2 to n minus 1. Okay, now what do I need to calculate here? I need to calculate t new at I, right? So I have already written it down here. T at I is equal to T old plus D into so and so term. Okay, T old of I plus D into, sorry, D into what do you say, T old at I minus 1 minus 2 times T old at I. First I am writing for normal FTCS, then I will go for Duport Frankel. Okay, T old at I minus 1. Sorry, this should be I plus 1, I plus 1 to T old at I. Okay, so this is done and dusted. Okay, so we have just done that. Here what do you say, space marching. Here we have done the time marching. So it is very important, this is a step which many people forget to do. You have to update, keep on updating t old and t new. Okay, now you have calculated t new using t old, that is tn. Okay, now you have to update, right? T old also will become t new now, because see, it's like this. You you went from here n to n plus 1 now. Now you will go to next time step, right? So there you have to go from here to here. So this n t, this I called it as t old and t new here. Now when I come here, okay, this t new will become t old. Okay, so t old I have to assign it to t new, and then again you calculate t new. Okay, so this is very important step. I have seen many people skipping this step. Okay, t old is equal to t new, I have to write this. Okay, before going to next time step, because after this I am going to next time step, na, tm plus tm delta t. Okay, so now this is done. This is just the code. Okay, this is all the code I have to write down. Okay, this is as simple as that. Okay, I hope you find it very simple. Okay, why it is showing error here, I don't know. Might be unused. It's not unused. Okay, okay, let us see. So plot x comma t new. Okay, and I need to define x also, sorry. Okay, ftcs simple. Okay, I need to define what is x also. Okay, x is equal to what? 0 to del x to 1. Okay, it's just array of that. Okay, 0 to 1 with the spacing of del x. Okay, I don't know why is this throwing this error. Anyway, let me see. Yeah, so you are getting something like this, right? Solution 100 and you have 0 at the right hand side. Okay, so what should be the ideal correct answer for this question? I mean, you already know, I think, the analytical result for this. So I have a plate, so it is at 100, this is at 0. How should be the final temperature variation? Can you write down on the chat box? Steady state, when it reaches the steady state. Okay, I'm not solving steady state equation anymore, first of all, but analytical result is steady state result. Oh, so how should it be? Can you write down on the chat box? With respect to x, okay, how should my temperature vary? Here it is 100, here it is 0 at x equal to 1. How should the temperature vary? It's a very, I think you might have all done this in the heat transfer course, I think. Can you write on the chat box? Ah, yes, very good. Straight line. Yes, it should be just a straight line. Okay, there will be a linear variation of temperature. That is the analytical result which you get for this equation. So just you can verify that also. Okay, steady state dou t by dou t is 0. Del square t by del x square is equal to 0. So what it will end up? T is equal to ax plus b, right? So it's a straight line. T is equal to ax plus b. So that is the steady state result. Now if I see this result, it's not a it's not a straight line here. Okay. Why? Can you write down on the chat box what might be the reason why I am not getting a steady state? I mean, sorry, why I am not getting a straight line? Can you just write down on the chat box? So just try to answer so that you will also learn something. Okay, and it will make something interesting. The course will be more interesting. Error, transient, error. Don't know. It might be error, but yeah, I am solving a transient equation and have stopped at t is equal to 10. Okay, I have forcefully stopped at t is equal to 10. Now just let me see what will happen if t is equal to 40. I am getting a different result, right? T is equal to 10. I was getting from zero point 0.3 only, it was going to 0. Okay, now it is at least coming till 0.6. Now let me go to 100. Yeah, now it is coming more of a straight line. Still it's not a straight line. Okay, now let me go to 200. Yeah, it's now more straight line. Now you can keep on doing this. Okay, 200, 300 and all, but the way in which we in CFD classically do is we do not forcefully stop it like this. What we write is while error is greater than some tolerance, keep on doing, but when error goes less than a tolerance, okay, when error goes less than this tolerance, okay, first let me define error is equal to 1 so that it just enters the loop, and then finally I'll make error is equal to 0. Now I typically calculate error. What is error? Error is t absolute of t new minus t old. Okay, so that is the error. It is actually divided by delta t, but let me ignore that. In actual case you have to do divided by delta t, but even ignoring that, okay, error is equal to 0 0.0. And t new and t old are anyway same here. Okay, it will come up to 0, but you have to do this before updating. Okay. Uh-huh. So what is it telling me? Be unused. Okay, let it be used. Okay, this is all not required, I think. Okay, fine. Okay, and it will give an array. If I do just t new minus t old, so I have to select maximum of t new minus t old. That is over the whole domain. What is the maximum? Okay, so now if I do this and write 10 raised to minus 6, whenever the difference between the two time levels, when it comes below 10 raised to minus 6, that is if you get 100.00001, 100.00015, okay, at that time it will stop. If it is 100.00002, then it will not stop. It will then again go to next time step. Okay, it will keep on doing that. Okay, so I am just stopping it like this. So this is how we usually stop if we know that the problem reaches a steady state. Okay, I think I ended up with some error here. F absolute is not there. Oh, max whatever. Max, max. I think I have to write only absolute or what. I usually use C, so in C we write F absolute. I don't know whether it is. Okay. Yeah. So this is the final answer. Okay. Uh, Now you can see that this is also not exactly straight. If I fit an exactly straight line, somewhere here near point 6, point 7, there is some deviation. It's a straight line, but it's not exact straight line. This is due to the errors. These are the errors which come in. Okay. So these are the discretization errors, truncation error, whatever error. Okay. So, but anyway, this is a straight line, or very to a larger extent, 99% it is straight line. Okay. So there are some errors, because of that we get that deviation. Okay. So this is how you do CFD. Okay. Now delta t I have taken 0.001. Okay. Let me take 0.01. What will happen? Still you are getting a straight line, but if you actually do an error analysis, you will see that error is a little bit increasing. Okay, now if I do error delta t of 1, it will happen. Okay, still I am getting the same straight line. Okay, so I have I don't know where it has stopped. Okay, but let me just check. Delta t is equal to 10. Oh, what happened? I don't know. T new. Huh. So you can see now when a delta t is equal to 10, when I took NaN infinity, so the solution diverged actually. Okay, so just let me take delta t is equal to 6. Somewhere it is diverging. Okay, now also it has diverged. Okay, so 4. Yeah, till 4 or 5 it was correct, and after that it has diverged when I increase the delta t. Okay, so why is this case? I'm using a simple FTCS scheme. What is the stability criteria of FTCS scheme? Can you write down on the chat box? You have done von Neumann stability analysis for a simple FTCS scheme, and what was the stability criteria for that? Can you write down on the chat box? D should be less than half. D is nothing but your this thing, alpha into delta t by delta x square should be less than half. You have done von Neumann stability analysis. Okay, so delta x is fixed, delta alpha is fixed. It is a property. Okay, delta x also you can change, but let us assume delta x is fixed. Okay, delta t should be less than some value basically. Only then it will converge. So when I went beyond 5, delta t, it diverged. Solution diverged because d is becoming greater than 1 by 2 there. Okay, so that is why you cannot take a larger delta t here. Understood? So these are schemes which are easy to write the code, but they will diverge. For a very large delta t, we have to select a very small delta t. These are what do you call it, as conditionally stable schemes. Okay, is this understood? Is this code understood? That is very important. Do you have any queries with respect to this simple FTCS scheme? I hope that this code was very easy. I mean, did you find anything which is difficult? I mean, just ignore this error thing, okay? You can stop it at some time also. That is also possible. Like how I had written initially, while time is less than so and so, stop it, okay? That also you can do. But this is the main crux. Is this? Did you find it easy or how? Can you write down on the chat box? How did you find out? Yeah, I will share this code with in the Google Drive where I have uploaded, where I usually upload the PPTs. I will upload the M file also, that MATLAB file. Okay. Okay. So you felt this easy, right? So this is the starting point. Okay. So you should feel easy. Otherwise, you cannot just go into CFDs all Navier strokes. Okay, just random directly you cannot go there. You should begin with these things. This is explicit time marching. Start with these things. You will ultimately be able to solve most challenging problems which are not available in a commercial software also. Because if you see in acoustics, which I mainly work with, the solution to many equations are not available in commercial softwares like COMSOL and ANSYS also. Okay, ANSYS anyway not available. COMSOL does have some I mean models for acoustics, but in some unsteady flow cases, the equations get changed, and that time you cannot sit with some software or do something. You will not get the correct answer, so you have to write the codes. Okay, and in COMSOL also they have given the option to write some codes. Or I don't know. So yeah, so this is the importance of writing codes for CFD, and if you want to really have go deep into this is the starting point, I would say. Okay. Yeah, so one more last thing we will see. Just by making small change in this code, can make it unconditionally stable. That is the final objective here. Okay, so I have just copy pasted the same scheme. Okay. Okay, I have copy pasted the same scheme. Only thing is we have to make it frank Dufort Frankel scheme. Okay, so as I said earlier, what is the main change in Dufort Frankel? Yeah, so this 2 into, sorry, here 2 into Ti is there, na? This Ti I write it as Ti at n minus 1 plus Ti at n plus 1 divided by 2. Understood? So Ti at n plus 1 here also it's there, Ti at n plus 1 here also it's there. So when you have to bring this particular thing to the left hand side. Okay, so what it will become is 1 plus this Ti n plus 1, it is 1 plus D, right? Because you have D here. This 2 and 2 will anyway get cancelled. Okay, so no problem. So 1 plus D into Ti at n plus 1 is equal to Ti at n minus 1 now. Here it is n minus 1 for, okay, plus D into this whole term, whatever is there. So that is the change. Okay. So this whole thing, whatever is there, I have to divide it by, I think, 1 plus D, right? Divide it by 1 plus D. And here 2 will not be there. Here and T old of old will be there. And here also T old of old will be there. Okay, this is the only one line change which I have done here. Okay, and also I think T old of old, you have to take it as T old. T old. Okay, so T old of old I am using at 2 points which you can see highlighted, right? This is Ti at n minus 1, the initial one, plus here in the central space for I only I am using that n minus 1, T old of old. Okay, otherwise I am using n only. Okay, and divided by 1 plus T. Okay, this convergence anyway it will remain same. Okay, this is the only thing. Okay, so now I have the scheme. So delta t is equal to 1. Let me check. Just let me check whether scheme is correct or not. Okay, so the scheme is correct. Okay, you are getting 100 to 1. So when I went to delta t is equal to 5, I think 6. Okay, there this FTCS simple was diverging. Now let us see what will happen with Dufort. So still you are getting a straight line, right? Whereas with this 6, if I put 6 in the simple FTCS, okay, sorry, what did I do? You ended up with a divergence. That is why you are not getting any values here. Okay, you will get NaN values. Whereas with the same delta t is equal to 6, I am able to get a straight line. Okay, so are you able to appreciate this point that even with a higher time step, I am able to get a comparable solution with the analytical one. Okay, still I am getting good solution with any delta t. I am not getting any divergence here. But you can see that if you really do an error analysis, this will actually, the error will go on increasing, especially for a complex problem. It will not be accurate, but it will be stable. Okay, so I hope you understood. Like, I only changed one line in this whole code to make it from FTCS simple to this Dufour Frankel scheme. Okay, only one line, and then I'm getting an unconditionally stable solution. So that is the whole beauty of this. Okay, so first you started with a simple thing. Always start with a simple thing, and then start changing that and make it more solid, make it more stable, and all those things you can do later on. Okay, I hope this was clear. Are there any queries regarding this week's content? And one of you, I don't know, MATLAB code I will give. Some other question was there. It would be helpful if you provide us the assignment for coding. Assignment for coding. I can give. There are like many questions, you can try to solve them. I mean, if you are interested, yeah, I'll post them also. Maybe in the PPT itself, I'll include them. Write some questions which you can solve. Okay. But apart from theory, learning theory is very important. I would not underscore that. But also doing something practical is much more important. I mean that when you do that, you will get an interest in theory also. That is what I have personally felt. I mean, the stability and all you are seeing, right? And I mean how beautifully it is changing. Then you go to von Neumann stability analysis, see why that is happening. Physical, you get physical intuition also why that is happening. We are trying to smoothen out the things. I think that is gone here. Okay, so that is why you are getting conditionally stable. So you will find it interesting to study that later on once you do this. Okay, so if there are any queries, you can just write on the chat box. Okay. Yeah, you can use very high time steps size. That is the main use. And when you use a very high time step size, the computational time will be less. So this was a simple problem. If you go to complex problem, it will take 1 day, 2 day, or something like that. So there you can bring down the computational time to a very large extent. Okay, by using such schemes, because you can now use higher computational time step size. But be very careful. You will not get good accuracy. Okay, if you can tolerate that loss in accuracy, then you can go with this default Frankel. Yeah, are there any queries? So I would like to ask one question, because we are already in week 3. ANSYS is not using, I don't know whether they use this scheme or no. I mean, you can check their manual. I don't think, I have not seen ANSYS people using uh, Dufour Frankel scheme or something. They use an implicit scheme. Again, you will study in the next classes that implicit, again, I think is a unconditionally stable scheme. Okay, we will see it next. It is a bit difficult to code. I mean, we have started, right? We can modify this code only. Okay, next week we will modify this only. We will come up with an implicit code. I think the ANSYS uses implicit code. I don't think they are using any explicit time matching or something. Okay, so that will be again unconditionally stable there. That is a much more with implicit you get unconditionally stable and you get more accuracy also. Both the things you get at one same. Okay. Yeah, I wanted to ask one question. See, I have maybe what I usually do is first I discuss the recap of the weekly contents like for half an hour or 40 minutes, something like that. Then I spend some, say, 30 minutes, something like that, on the question and answers. Okay. And then maybe 30 minutes on code. So that is how I have planned. Do you think that I'm giving like less time for question and answers and more time for this revision and coding? You may feel free to give comments on that. Okay. I mean, do you want me to really solve more of this coding problems, or do you want me to solve more of those assignment question and answers? That is what I want to know. And should I reduce the theory for the first 30 minutes or so, something like that? I give a brief recap. So, should I increase the question and answers? Can you just write on? Okay, theory required. So, because I think that, see, one thing is you people are hearing this. Many people will see these videos on YouTube. So, they might have not gone through the weekly content, or they might be not in this course, first of all. They might be just seeing something for understanding purpose. So, they might not be knowing. So, that is why I take those people also into account. Okay. So, that is why I give 30 minutes, 40 minutes for theory. Okay. More of assignments. If it's clear, we can try coding better. Just let me unmute and allow you to talk because I did not understand. Uh, yeah, can you unmute yourself and speak? Yeah, good evening. Good evening. Theory I'll be dealing with, but do you want me to have more assignment questions and less coding, or how is that? Theory I'll be doing, okay. Okay, so after some time, more assignment questions I have to solve. Okay, fine. Okay, so when the complexity increases, you are telling assignment questions I need to go in because these are simpler assignment questions. Okay, okay, fine. Yeah, I will do that. One more thing which I am getting idea now is I'll mainly concentrate on difficult questions. Okay, I'll mainly solve that. Easy questions I will not do. Okay, yeah. Thank you. Any other feedback? Huh. Okay, 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 fine. But with coding, I'll do simple things only. I'll not complex coding. Any other feedback? Yeah, hello. Hmm. That's a very good point. Actually, I was thinking about this just before the class started. Yeah. I will think about this. Yeah. So whenever we do some example, I will try to take it as a practical example, like in real life situation. That example, what are the dimensions and all. So then we can try to solve the theory also and solve that code also, so that it will give a more physical intuitions. That is what you are training, right? Like the dimensions and all, whatever it is there. Pardon, I did not get you. In theory, you have some. Ah. Hmm. Okay, so maybe I can do one thing because I have not got that much time. So these things I can give it as some problems, and then maybe you can. I will just give the hint also how you can implement those things, boundary conditions and all. But as the course goes on, this was the first session, so I did not really get into that. But as the course goes on, I will just discuss those things also. Okay, boundary condition implementation and whatever in theory you have queries. Okay. Okay. Okay, I'll try to link these things with the practical cases. Okay, so that is even that I had it in my mind just before this class, but yeah, from next week let us try to do that. Yeah. Okay, any other queries? If not, we will meet next week. Okay, next Tuesday. We'll still again solve this code as well as the assignment question. And these codes anyway, I'll upload it on the Google Drive. Okay, along with the PPT. Okay, if there are no queries, you can leave the meeting. Okay, we will see you in the next class. Thank you. Thank you for attending. Okay. Okay, thank you. Thank you.